Hello, in this video we're going to go over the solution to a final exam from 2022 for multivariable calculus and linear algebra. So here is the first question. Evaluate the determinant of the following 3 by 3 matrix using row operations. And we must only use row operations. So what we do is we're going to apply row operations, and in every step we are going to consider how that changes the determinant. So let's just start from the original determinant. We will apply row operations. We will do row 2 minus row 1 and row 3 minus row 1. So that does not change the determinant. So that would be determinant of 1a squared, and then we are subtracting row 1 from row 2. So this would be b minus a, b squared minus a squared, and then 0 c minus a, c squared minus a squared. Now we will apply a row multiplication. So we will factor b minus a. So this would be basically 1 over b minus a times row 2 and 1 over c minus a times row 3. Except you could kind of think about that as going backwards. Essentially we can do b minus a times c minus a times determinant of 1a squared, 0 1 b plus a, and 0 1 c plus a. If the denominator of b minus a makes you a bit uncomfortable, which it does make me uncomfortable a little bit, I would think about this one as going backwards with the operation b minus a times row 2, and also c minus a times row 3. So this is better because that would avoid denominator of 0 at the bottom. Now we are going to make this entry 0. So that gives us row 3 minus row 2, and that would become determinant of 1a squared, 0 1 b plus a, 0, and when we subtract row 2 from row 3 we get 0 here, and this gives us c minus b. Now we will factor b minus c, so it would be kind of going backwards. It would be c minus a row 3. So this gives us b minus a times c minus b, c minus a times c minus b, and then determinant of 1a squared, 0 1 b plus a, 0 0 1. And finally we'll have to make these entries all 0 in order to get to the identity matrix, and we can do that by doing row 1 minus row 2 and row 1 minus so I guess I'll do the first thing that we're going to do is we're going to do row 1 minus a squared row 3 and row 2 minus b plus a row 3. That gives us b minus a, c minus a, c minus b times determinant of 1a 0, 0 1 0 0 0 1. And finally we will do the last row operations, which is row 1 minus a row 2. That gives us b minus a, c minus a, c minus b, and the determinant of identity, which is 1 by definition. So the answer becomes c minus b minus a, c minus a, c minus b. So that's our final answer. Okay, so the next problem is determine if the function t from R2 to R2 given by this is linear. So clearly the first one appears to be linear. The second one is a product, so that doesn't seem to be linear. So all I need to do is to give an example that doesn't make this linear. So you can think about t of perhaps 1 1. T of 1 1 is equal to, so we're going to plug in x and y equals 1. We get 3 comma 1. T of 2 comma 2 would be, if I replace x by 2 and y by 2, that gives me 6 comma 4. and 2t of 1, 1 would be 6, 2. So now the result is t of 2, 2 is not the same as 2t of 1, 1, and therefore t is not linear. So if we do this right, this is really the only thing we need to do. We don't need to check both conditions. We only need to give one counterexample and then show that this is not linear. If we want to show it is linear, if you want to show a function is linear, we'll have to go through the process of checking that it satisfies additivity and it satisfies homogeneity. But if you want to show something is not linear, one example that violates one of the conditions is enough. Next is an epsilon-delta problem. So I will do the sketch first and then we'll write down the solution. Using epsilon-delta definition of limit, prove that the limit of xy as xy approaches 1, 0 is equal to 0. So this is what we need to show. We need to show for every epsilon positive, there is a delta positive that whenever x minus 1 squared plus y minus 0 squared in square root is less than delta, then the distance between xy and 0 is less than epsilon. And this would have to be positive, but in this case we know it doesn't matter if it is equal to 0 either. Now, from the assumption, we know that x minus 1 is less than delta and absolute value of y is also less than delta. And we want to go from here to absolute value of xy less than epsilon. We know that absolute value of y is less than delta, so we'll start with that. So that gives us delta. But I need to be able to control absolute value of x. In order to be able to control absolute value of x, I will make sure that delta is small. So let's say delta is less than 1. So that tells us absolute value of x minus 1 is less than 1, which means x is between 0 and 2. So that tells us absolute value of x is less than 2. So that means absolute value of xy is less than 2 delta. And if I make sure this is less than or equal to epsilon, and also make sure that delta is less than 1, then I would be done. Or even equal to 1 would be fine. So that tells us delta must be less than or equal to epsilon over 2 and less than or equal to 1. So we just take the minimum of these two. Here is how we're going to write down the solution. The first sentence would be let epsilon be positive. And then we set delta to be the minimum of 1 and epsilon over 2. First of all, since epsilon is positive, since epsilon over 2 is positive, and 1 is also positive, delta would be positive. Because in the definition of epsilon delta limit, we have to make sure that delta is positive. Now, if the distance between xy and 1, 0 is less than delta, then square root of x minus 1 squared plus y squared is less than delta, which tells us absolute value of x minus 1 is less than delta and absolute value of y is also less than delta. So we know that delta is less than or equal to 1, so that means x minus 1 is less than 1, which means x is between 2 and 0, which means absolute value of x is less than 2. So that means absolute value of xy minus 0, which is absolute value of x times absolute value of y, is less than, absolute value of x is less than 2. Absolute value of y is less than delta, so that would be less than delta. And I know that delta is less than epsilon over 2, less than or equal to epsilon over 2, because of the way we chose it. We chose it to be minimum of 1 and epsilon over 2, which is delta. So that tells us absolute value of xy minus 0 is less than epsilon. And that tells us the limit of xy as x and y approach 1, 0 is in fact equal to 0. Number 4, let f from R to R be a differentiable function. Define g of xy equals f of x plus y over x minus y. For every x not equal to y, we want to prove the equality that is given. So this problem is a chain rule problem. So if we call this one u, x plus y over x minus y, u, then we see that this function is a function of u, and u is a function of x and y. So what we can do is we can say derivative of g with respect to x is equal to f prime of u times partial of u with respect to x. So let's evaluate this one. This is equal to f prime of u times partial of u with respect to x is, the denominator is x minus y equals squared, and then we use the quotient rule, derivative of numerator, which is 1 times denominator minus derivative of denominator times numerator, and then over denominator is squared. So that's f prime of x plus y over x minus y times x minus y squared at the bottom, and then the x's cancel, we get negative 2y. So that's partial of g with respect to x. Partial of g with respect to y is equal to f prime of u again, and then partial of u with respect to y. And if you want to see what the diagram is, this g is a function of u, which is equal to f of u is a function of u, and u is a function of x and y. So when you want to find the derivative of g with respect to x, you'll have to go this route, and if you want to do the other one, you'll have to go this route, which is why you have only one term in the chain rule. So that's f prime of u, derivative of u with respect to y. We have x minus y squared at the bottom, derivative of numerator times denominator minus derivative of denominator times numerator, and this is equal to, we have x minus y squared at the bottom, and then here we have negative y, we have plus y here, so those two cancel, this negative y and plus y cancel, and we get 2x on top. Now when you evaluate x, g sub x plus y, g sub y, we get f prime of, well, there is also an f prime of u here, f prime of x plus y over x minus y times negative 2xy over x minus y squared plus f prime of x plus y over x minus y times 2xy. So we multiply g sub y by y divided by x minus y squared, and clearly that's 0, which is exactly what we wanted to prove. So let's look at number 5. Let S be this set of all points in Rn that satisfy an equation. We want to determine if S is compact and if S is in fact open. So in order to show something is compact, we will have to show it is bounded and also closed. So this is clearly bounded because all of these xi's are less than 1, because all the exponents are even. It is also closed because this function is continuous, so it should be compact. So S is compact. Here is why. If you look at absolute value of xj, absolute value of xj is less than or equal to 1 because xi squared, xi to the power of, 2i is greater than or equal to 0 for all i. So that tells us, if I look at x1 squared all the way to xn squared, square root of that, that is going to be less than or equal to square root of n. And that is less than, you could just do 2 square root of n. So that tells us x1 through xn is in fact in the ball of radius 2 root n centered at the origin. So this tells us S is in fact bounded. Now we will take a function that gives us x1 squared all the way to xn squared, xn to the power of 2n equals 1. So it gives us that as a pre-image. Let, I called it f from Rn to R be given by f of x1 through xn equals x1 squared, x2 to the fourth, all the way to xn to the power of 2n. Now f is continuous because it's a polynomial. So that tells us that inverse image of every closed set is closed. Now we know that by an example, the set containing 1, every finite set, is closed. So by a theorem, f inverse of 1 is closed. And then by definition of pre-image, S is equal to f inverse of 1. So that means S is closed. So we showed that S is closed and bounded, therefore S is compact. So therefore S is closed and bounded, which means it is compact. Okay, so that's the first part of the problem. The second part is asking us to show if it is open or not. So since there's a boundary here, it doesn't appear to be an open set. So we will claim that S is not open. So we will show S is not open. We'll take a point on that set. So note that if you take 1, 0, 0, 0, this is inside S. Now we will take an open ball around this point, and we will show that there is something inside that open ball that is not inside the set. So consider any positive radius. We will show that ball of radius r centered at this point is not a subset of S. So we will have to find a point inside this ball that is not in S. So consider this point. If you take 1 comma r over 2 and then 0, 0, 0. First of all, the distance between this point and the center 1, 0, 0 is square root of 1 minus 1 squared plus r over 2 minus 0 squared, and then the rest of them are 0, which is r over 2, which is less than r. So this means the point 1 comma r over 2 comma 0 is in fact in the ball of radius r centered at 1, 0, 0, 0. However, this point is not in S, because if you look at 1 squared plus r over 2 to the power of 4 plus 0 to the power of 6 plus etc. 0 to the power of 2n, this is 1 plus r to the fourth plus 16, which is more than 1. So that tells us this point 1 r over 2, 0, 0 is not in S. So this means the ball of radius r over radius r centered at 1, 0, 0 is not inside S, and that means S is not open. And that completes the solution for this problem. Okay, let's move on to the next one. Consider the quadratic form this. Write down the matrix of this quadratic form and use this matrix to determine if the origin is a local minimum, a local maximum, or a saddle point. So here is the solution. We're going to take this matrix corresponding to, I'm going to call that A, corresponding to this quadratic form. The diagonal entries are going to be the coefficients of x squared, y squared, and z squared. That would be 1, 4, and 3. Off diagonal entries are going to be negative 1 here. We'll have to take the coefficient of xy divided by 2, put it on the off diagonal entries. Xz is negative 1, so that would be negative 1/2 here. and then coefficient of yz is -4, so that would be -2. Now we will have to check whether all the eigenvalues of this are positive or negative, or some positive, some negative. If you recall, there was also a shortcut. We could find those deltas and check whether they are positive or they are alternating. That would be an alternate method. So let's evaluate that. Delta 1 is 1. It's the determinant of this one, which is just 1. Delta 2, which is positive, so that shows that it may be positive definite. Delta 2 is determinant of 1, -1, -1 and 4, which is 4 minus 1, which is 3. That's also positive. Finally, delta 3 is determinant of A. So we'll have to evaluate that one. We will expand along one of the rows, let's say the first row. So it would be 1 determinant of 4, -2, -2, 3, minus -1 determinant of -1, -2, -1/2, 3. So we are doing the determinant along the first row, and we get 1 times determinant of 4, -2, -2, 3, minus 1 times determinant of -1, -2, -1/2, 3, and then plus -1/2 times determinant of, we'll have to eliminate the last column and last row, -1, 4, -1/2, -2. Let's evaluate this one, and we really only need to see whether this is positive or negative, so we don't have to completely evaluate it. So this is 12 minus 4 plus -3 here, and then -1. Okay, so we have that, and then the last one is -1/2 times 2 plus 2, I believe. Let's simplify this. 12 minus 4, that's 8, minus 4, that's 4, and then -2. So that's actually 2, which is positive. So since all of these deltas, delta 1, delta 2, and delta 3 are all positive, quadratic form is positive definite, and therefore 0 would be a local minimum. So 0 is a local and global, in fact, minimum for this quadratic form. Okay, let's move on to the next one. Consider the parallelogram region whose vertices are 1, 1. We'll draw a diagram for this. Very important to always draw a diagram for these problems. So 1, 1 right here. So I'm going to mark it as 1, 1. 2, 2. We mark it here. 5, 2. So 3, 4, 5. So 5, 2 is here. And finally 6, 3. So we have this parallelogram. And then 3, so 6, 3, somewhere around here. So this is our parallelogram. And we're asked to evaluate an integral over this region. Okay, so clearly we can do that by breaking this up into 2 different regions. If I call this one R, R can be broken into 2 elementary regions. But that may not be the wisest thing to do, because you see that it's going to be a little bit complicated evaluating the integral. And the integrand is also not very simple if you break it up into 2 different regions. A better approach would be to use a change of variables here. So if you look at the 2 sides of this, this one is y minus x equals 0. This one is y minus x equals -3. So the first one is 5, 2. That satisfies this equality. The second one is 6, 3, and 3 minus 6 is negative 3. So that's one appropriate change of variables. So this side is going to have a slope of 1/4, so it would be 4y minus x equals, if you plug in 1, 1, you get 3, and if you plug in 5, 2, you are also going to get 3. The other side is 4y minus x equals, if you plug in 2, 2, you get 6, and if you plug in 6, 3, you are also going to get 6. So these are the sides of the parallelogram. So we'll do a change of variable. U equals 4y minus x, v equals y minus x. And notice that the integrand is continuous, and u and v are completely, in fact, they are c infinity. So u, v are c infinity, so is the integrand, because inside this region 4y minus x is positive in the region. So the natural log has a positive number inside. Inside natural log, we are taking the natural log of something positive. Now we're going to do a change of variable here. Now we're going to have to evaluate the Jacobian of xy relative to uv. This is 1 over Jacobian of uv relative to xy. So this would be 1 over, we'll do the Jacobian of uv. So determinant of, we'll do derivative of u and v with respect to x and y. So this is determinant of derivative of u with respect to x is negative 1. Derivative of u with respect to y is 4. Derivative of v with respect to x is negative 1, and this one is 1. We will evaluate that. We get negative 1 plus 4, and that is 1/3. Now we'll have to take its absolute value, but of course this is positive, so we don't need any absolute value. And what we're going to do is we're going to do the surface, the double integral over the region y minus x squared natural log of 4y minus x dA is equal to, so that was what we were given, is equal to. So we are going to switch to uv. Y minus x is v, so we get v squared natural log of 4y minus x is u, and then we're going to do du dv. Now we know that the limits for u and v are 0 to negative 3 for v, so negative 3 to 0 for v, and for u it is 3 to 6. And this is pretty easy to integrate. So we get integral from negative 3 to 0. Now we have to do integration with respect to u. You could do integration by parts, and if you remember, integral of natural log of u is u natural log u minus u, and that's from u equals 3 to u equals 6, and then dv. So integral of natural log u is u natural log u minus u, because if you differentiate this, you get 1 times natural log u plus u times 1 over u, and then minus 1. Okay, so we're going to plug that in, and if you don't remember that, you can do this just the integration by parts method. So this would be integral from negative 3 to 0. We're going to plug in 6 and 3. We get v squared times 6 natural log 6 minus 6 minus 3 natural log 3 plus 3 dv, which is equal to, okay, so we have v squared negative 3 to 0, v squared times negative 6 and 3 become negative 3, and then 6 natural log 6 is 6 natural log 2 plus 6 natural log 3 minus 3 natural log 3 dv, and then we're going to integrate with respect to v. We get v cubed over 3 from negative 3 to 0 multiplied by 6 natural log 2 plus 3 natural log 3 minus 3. And then we can evaluate that pretty easily. We can plug in 0, we get 0. Plug in negative 3, we get negative 3 cubed, which is negative 27 over 3. That is 9 times this quantity, 6 natural log 2 plus 3 natural log 3 minus 3. And that would be our answer. Find the volume of the solid region in R3 that lies inside the sphere, this, and above this cone. Okay, so let's first draw the region as usual. So x squared plus y squared plus z squared minus 2z equals 0. We can complete the square. We get x squared plus y squared plus z minus 1 squared equals 1. So this is a sphere of radius 1, centered at 0, 0, 1. And the other one is a cone, so we know how it's going to look like. Vertex of the cone is at the origin. So the center is right here. This is the z-axis, y-axis, and the x-axis. And then we are looking at this region right here, because they said inside the sphere and above the cone. So this is the region. Now, we can do that using both cylindrical coordinates and spherical coordinates. I would guess that spherical coordinate would be better because of the fact that we have a cone involved and we have a sphere. So let's try spherical coordinates. So we'll have to find the limits for rho. So rho goes from here to the sphere. So we'll write down the sphere in spherical coordinates. So sphere is x squared plus y squared plus z squared, which is rho squared, equals 2 times z, which is rho cosine of phi. From here we get rho equals 2 cosine of phi. That's the maximum. And rho equals 0, which is the minimum. Now, for finding the minimum and maximum value of phi, we'll have to find the phi on the cone. So the cone is given by z equals r, because it's the square root of x squared plus y squared, which is rho cosine of phi equals rho sine of phi. And that gives you tan of phi equals 1, which means phi is pi over 4. And that gives you the maximum and minimum for phi. Minimum is 0, maximum is that. So volume would be the triple integral over the solid, let's call that E, of 1 dV, which is equal to, so integrand is just 1. We'll have to put the spherical factor, rho squared sine phi, d rho, d phi, and d theta. Rho goes from 0 to 2 cosine of phi. Phi goes from 0 to pi over 4, and theta goes from 0 to 2 pi. We will have to evaluate this integral. Sometimes they might tell you to stop when you get an iterated integral, but here they didn't, so we actually gonna have to do the calculation. So 0 to 2 pi, 0 to pi over 4, rho squared sine phi, d rho, so that would be rho cubed over 3 sine of phi, and then we'll have to plug in rho equals 0 and rho equals 2 cosine of phi, d phi, and d theta. We're going to now just plug it in and then do the other two integrals. They shouldn't be that difficult. Integral from 0 to 2 pi, integral from 0 to pi over 4. So we're going to plug it in. We get 8 cosine cubed phi sine phi over 3 d phi d theta, because when you plug in rho equals 0, we're just going to get 0. Now here you can either do a u sub for cosine, or you can probably eyeball what this integral would be. So integral would be 2/3 cosine to the power of 4 of phi. except you have to have a negative sign in front. If you take the derivative of cosine to the power of 4, you get 4 cosine cubed times negative sign. And then we have to evaluate this from 0 to pi over 4, of course, for phi. And then we'll have to do d theta. Integrand is a constant, so when you do d theta, you're just going to get a 2 pi in front. So 2 pi times negative 2/3 times cosine to the 4th of 1 pi over 4, which is 1/4, because cosine of pi over 4 is 1 over root 2, and then you square that, you get 1/2, and you square it again, you get 1/4. Minus cosine of 0 is 1, so we get that. So this would be 4/3 pi times 3/4. So interestingly, the answer is in fact just pi. Okay, and yeah, notice that this negative sign cancels with the negative sign for this one. So they're both negative, which makes sense because we were trying to evaluate a volume. Okay, so next problem. Use the Stokes theorem to find the work done by the vector field this on a particle that moves along the line segments 0, 0, 0, 1, 1, 1, and then to 0, 0, 2, and then back to the origin. Stop when you get an iterated double integral. Okay, so let's look at the origin 0, 0, 0. Then we have a point 1, 1, 1, which is in the first octant. Then we have the point 0, 0, 2, so a point right here, and then we go back to the origin. So this is the curve that they gave us, and the direction goes this way. They specifically told us that we have to use the Stokes theorem, so we really don't have a choice. So we will have to find a surface whose boundary is this curve, and the obvious surface would be this surface. Let me call that sigma. So we'll have to use that sigma as our surface. So what we know from Stokes theorem, and notice that this vector field is C infinity, so we can apply Stokes theorem. So what we're gonna have to do is now we have to find a surface integral over this surface. So the line integral of f, so they said work done by this vector field, which is the same as a line integral. This line integral over this curve C, I will denote that curve by C, is the same as the surface integral of curl of f dot ds. So these two are the same. This is the Stokes theorem. As long as we make sure that the two orientations match. Now, orientation for sigma, when we look from forward, it is in fact counterclockwise. So orientation for sigma would have to be also coming out of the board. So the orientation for sigma is coming out of the board. So first we need to find an equation for sigma. So the points on sigma are 0, 0, 0, 1, 1, 1. So we can find two vectors, 1, 1, 1, and 0, 0, 2 are vectors on sigma. In order to find that perpendicular vector, we will have to find the cross product of these two. So we will do 1, 1, 1 cross with 0, 0, 2, and we'll have to evaluate the determinant of I, J, K. That's like basically how we find the cross product. And then we have 1, 1, 1, and then we have 0, 0, 2. So this would be equal to, so it would be 2i. So we have I times the determinant of the rest, and then minus, so 2j, and then finally 0k. So that is our normal vector, and then we'll have to take this and the equation would be 2 times x minus one of the points. I'm going to take the origin minus 2 times y minus 0 equals 0. So this tells you that the equation of the plane is in fact x equals y, which makes sense because the 3 points are 0, 0, 0, 1, 1, 1, and 0, 0, 2. So all three of them have this x equals y. So the equation of the plane is in fact x equals 0, x equals y. So because of that, we can parameterize it with perhaps x and z, or maybe y and z. Either one doesn't really matter. So we can parameterize sigma by, let's call that maybe r of x comma z. It would be x comma x comma z. Now we will have to find out what are the limits of this, find the normal vector, and then go from there. So what are the limits of x and z? We'll have to find the projection of sigma onto the xz plane. So we're going to have to project sigma onto xz plane to see what we get. So xz plane, the points were 0, 0, 0. So if you eliminate the y coordinate, you get the origin. 1, 1, 1, which would be right here, and the other one was 0, 0, 2. So if you eliminate the y coordinate, you get this. So this is the projection onto the xz plane, and this one is 1, 1. So this is the projection onto the xz plane, which is in fact, you can parameterize this vertically. So in this region is given by the two lines are, so z goes from bottom is x and top is 2 minus x, because the two lines are z equals x and x plus z equals 2, and then x goes from 0 to 1. So these are the this is the parameterization of the projection onto the xz plane. Now we will have to find the curl and also find the normal vector to that sigma. So let's evaluate Rx cross Rz. So this would be the determinant of I, J, K. Rx is 1, 1, 0, 0, 0, 1. We will evaluate that. So when we evaluate this, we get I. So we get I times the determinant of the rest, which is 1, minus J, determinant of the rest, which is also 1, and then 0k. So this would be the cross product of these two. Then we'll have to check the orientation. So we'll have to see if the orientation matches this. Does it come out of the board? And the answer is yes, because coming out of the board means it is in the positive x direction. So and we will have to check that orientation. Matches the orientation. Next, we'll have to find the curl of that vector field that they gave us. So curl of f is going to be determinant of I, j, k, partial with respect to x, y, and z. And then we had e to the x plus z, xz, and 1. So e to the x plus z, xz, and 1. So I times, so the first determinant would be 0, partial of 1 with respect to y, which is 0, minus partial of xz with respect to z, which is x, minus j times partial of x with respect to x, 1 with respect to x, which is 0, minus 1, and then finally plus k times partial of xz with respect to x, which is z, minus partial of e to the power of x plus z with respect to y, which is 0. So this is curl. We have to find the dot product of this one. So the line integral of f dot ds is equal to surface integral of curl of f dot d capital S, which is equal to, so we found the limits of integration as 0 to 1, x to 2 minus x. Then we'll have to find the curl, which is negative xi plus j plus zk, and find the dot of that with I minus j, which was rx cross ry. We found that here. This is the normal vector. And then this is dz dx. And I believe they said you can stop after you find an iterated double integral. Yes, so we will do the dot product and then we'll stop. So 0 to 1, x to 2 minus x, and then we get minus x minus 1, so that's the dot product, and then dz dx. So that's just the answer. So that's a pretty easy integration. Okay, so problem number 10. Let E be a solid region in R3 whose boundary sigma is smooth and is oriented outward from E. Prove the following surface integral only depends on the volume of E. Okay, so for this problem, because it's a closed surface, they said it's a closed surface because they said it's the boundary of a smooth, it's a boundary of a solid region. So because it is oriented outward, we can apply divergence theorem or Gauss's theorem without having to worry about a sign. So by the divergence theorem, the integral, surface integral minus y e to the z plus sine of x squared j plus e to the zk dot n ds is the same as surface integral, let's call that E, I think they actually did call it E, of divergence of this. So divergence of this is 3 minus e to the z. If you take the derivative of this with respect to y, you get e to the z, and there's a negative sign. And then plus derivative of that with respect to z, you get e to the z, and then dv. Since the orientation is outward, we don't need to worry about a negative sign. And this is exactly 3 times the volume of E. So the only thing I need to worry about is that, in fact, the integrand is, in fact, C infinity. So note that the vector field is, in fact, C infinity. So I can apply divergence theorem. Finally, I had a bonus problem in that exam, which is usually the case. I usually have a bonus problem at the end of the exam. Here's the bonus problem. Prove that there is no inner product on R2 that gives us the norm this. So one of the things that we have done is the parallelogram identity. So we have shown that if this is a norm obtained from an inner product, then we have the parallelogram identity. So the norm of x plus y, which is one of the diagonals of a parallelogram, squared, plus norm of x minus y squared, which is the other diagonal of a parallelogram, is equal to twice x squared plus y squared. So this is something we have done before. So now we're going to show that in fact this is not true for this particular norm. So if it were to be coming from an inner product, we would have to have this equality. Now for that you'll have to come up with some kind of guess and check to see what would or would not work. So let's try something, and maybe the first thing that you would try, it may not work. So let's try maybe 1, 1 for one of them, and perhaps negative 1, 1 for the other one. So if you take x equals that and y equals the other one, we will get x plus y is the sum of these two is 0, 2, and x minus y is going to be, so we'll have to subtract, so we get negative 2, 0. Okay, let's evaluate norm of x. Norm of x is 1. Norm of y is also 1. Norm of x plus y, because they told us it's the maximum of the absolute values, that's 2. Norm of x minus y, that's also 2. So let's plug it into the equality, see what we get. So one side is norm of x plus y squared plus norm of x minus y squared. The other side is 2 times norm of x squared plus norm of y squared. And of course these two are not the same. So that means this cannot be obtained from an inner product because it doesn't satisfy the parallelogram identity. And that brings me to the end of this exam.